rice, yam, plantain, sugar, glucose. What do all these have in common? They are all carbohydrates. This is Unit 1, BIO216. We are going to learn about carbohydrates, their functions, their properties, and many more. You are welcome. I'm your facilitator, Drag Aleto. So you're welcome to Bio 216, Chemistry of Carbohydrates, Lipids, and Nucleic Acids. Like I said, I'm Dr. Udrak Aleto. In Unit 1, we'll look at carbohydrates, physical properties, and functions. Now, what do we mean by carbohydrates? The term carbohydrate describes a group of organic compounds ranging from simple sugars. What do we mean by simple sugars? The glucose you lick through polysaccharides. That's the garri you drink. The starch you use to starch your clothes. All these are what we call carbohydrates. At the end of this class, you should be able to define the term carbohydrates. You should be able to classify carbohydrates into the major classes. That's list the major classes of carbohydrates, list the properties of carbohydrates, highlight different roles played by carbohydrates in living things or living system, and explain the stereochemistry of carbohydrates. Now, what do we mean by carbohydrates? Definition of carbohydrates. Carbohydrates can be defined as polyhydroxy, aldehydes or ketones, or as substances that yield one of these compounds on hydrolysis. When you see this term polyhydroxy, what are we talking about? Poly means many, as we all know. Hydroxy, you can see this structure I have here. You can see all the hydroxy groups there. So polyhydroxy of aldehyde. This particular structure is an aldehyde or ketones. If you go back to your chemistry, you will realize that you would have studied aldehydes and ketones. So compounds that have or yield these things when they are hydrolyzed are called carbohydrates. What is the formula of carbohydrates? From your primary school, you must have been told that carbohydrate is CH2O bracket N. Yes, CH2O bracket N. But that's not all it takes. Not everything that has CH2O bracket N can be called. Not every carbohydrate has this formula. CH2O bracket N, where N is greater than 3. There are some substances that do not conform to this formula because they may have other elements like nitrogen, phosphorus, or sulfur. Some even have deoxy sugars. Like when you think of your DNA, but all these things still are classified as carbohydrates. So, in other words, all carbohydrates do not have the formula CH2O bracket N. Carbohydrates can be classified as monosaccharides, oligosaccharides, or polysaccharides. Mono means one, Oligo means few, and poly, like I said earlier, means many. And saccharide comes from the Greek word saccharon. So when you say monosaccharide, we are saying, and saccharon, sorry, and saccharon means sugar. So when I say monosaccharide, I'm saying one sugar. Oligosaccharide, few sugars. Polysaccharide, many sugars. Why are these so? Some carbohydrates like glucose contain only one sugar moiety in them, but some can have more than one, joined together by glycosidic bonds. When this happens, you have disaccharide. For example, we have sucrose. Sucrose contains glucose and fructose joined together by glycosidic bond. When this happens, it is called disaccharide. And as you can see, di also contains few saccharides, so it's still under oligosaccharides. Then we have polysaccharide. When we have up to 20 of these sugar moieties coming together, joined by glycosidic bonds to form a compound, we say it is a polysaccharide. That's how where starch, glycogen, cellulose come in. They are all examples of polysaccharides. What does carbohydrate do in nature? What does carbohydrate do to me? What does it do in my body? What does it do in the body of plants? What does it do to plants? What does it do to even microorganisms? All these are under roles of carbohydrates. One of the primary roles of carbohydrates is that they serve as nutrients to the cell. The brain, for example, can only use glucose as a source of nutrients. Glucose. And glucose is a carbohydrate. So the primary role of carbohydrates is to serve as nutrient. No matter how much fufu, how much rice, how much what else? Semo you eat, everything will be broken down to glucose. It is glucose your body can use, not the fufu you eat. The fufu you eat must be broken down to glucose for your body to be able to use it. Now, another role of carbohydrates is that it functions as a store of energy in cells. Carbohydrates gathers whatever we have eaten that we don't need. All the energy we have gathered in the fufu we have eaten, all the energy we have gathered in the starch we have eaten, and store them for us. As animals, the carbohydrate stores for us in form of glycogen. So we have glycogen stored and can be broken down to glucose when we need. For plants, carbohydrates will store their own for them as starch. So the storage forms of carbohydrates in animals is glycogen, whereas in plants is starch. So carbohydrate is a storage form of energy. Also, is a structural component of cells and tissues. Look at this insect I have here, and the other insect you also know. Look at cockroach, for example. You see that waterproof brown covering of cockroach. It is also a form of carbohydrate. It is called chitin. So it is a storage component, it's a structural component of cells. Also in plants, carbohydrate is there as cellulose. Cellulose is what gives plant cells rigidity. and it's a form of carbohydrate. Next, carbohydrate also plays important role in blood group. At one time or the other, you must have seen somebody who needs blood and say, oh, he's O positive. Oh, he's O. His blood group is O. His blood group is A. His blood group is B. His blood group is AB. What makes one blood group A, another one B, another one O, or another one AB, is the presence of some types of carbohydrates and proteins on the surface of the blood cell. From the diagram you see here, you can see I used blue to represent antigen A and B, green to represent antigen B. So carbohydrates in form of galactose and fructose function as antigenic determinant of blood group, ABO system. You can see it. Because this person has this carbohydrate blue on the surface of his blood cell, the person is said to be O positive. You can see this one has green carbohydrate green on the surface. The person is said to be B, a member of blood group B. You see this one has AB has both the green and the blue, and then O has nothing, no antigen. So these are the things that, so carbohydrates serve as the things that determine your blood group system. Also, apart from that, carbohydrate also functions as a lubricant. Imagine how your body will be if the bones in your joint are just rubbing on each other. When this happens, if it happens, you can imagine how uncomfortable life is. So carbohydrate acts as a shock absorber on your joints, in your joints. The carbohydrate there is called hyaluronic acid. It serves as a lubricant, and due to its viscous nature, and is there to support your joint. You can see this joint here, hyaluronic acid. You must have heard about the synovial fluid. It contains hyaluronic acid, and hyaluronic acid is also a carbohydrate that helps your body, serves as a shock absorber in your joints. Apart from that, carbohydrates also has physical properties. I don't want to make it look so scientific. When you look at carbohydrates, what do you see? If you see starch, you will see that it is white, isn't it? If you see sugar, if you see glucose, you see that it is white too. So some carbohydrate, and then if you put glucose in water, it is soluble. So you can say monosaccharides are soluble in water. Whereas if you put starch in water, it is not soluble, but it's also soluble in some other substances. So monosaccharides are soluble in water, but polysaccharides are like cellulose are insoluble in water. Carbohydrates also are solid at room temperature. Both the monosaccharide, oligosaccharide, that's why you can see your sugar, you can see your glucose, you can see your starch. They are all solid at room temperature. Carbohydrates, most monosaccharides and disaccharides are sweet to taste. You have tasted the sugar. Did I forget to tell you that the sugar we use to drink tea is a carbohydrate, and it's called sucrose. It's a disaccharide. So they are sweet to taste. Carbohydrates monosaccharides are crystalline solids. Monosaccharides, polysaccharides, and disaccharides are odorless. Now, I want us to think about what we have read, and I'll give you a class activity. And I want you to write it, answer the question quickly. State 3 functions of carbohydrates in nature. Good. I want to believe that you must fine. Good. Let's continue. Now let's go to another part of our topic. Stereochemistry of carbohydrates. Like I will say again, I will refer you back to the chemistry you did, the organic chemistry you did in secondary school and also in your year 1. Stereochemistry. Carbohydrates as organic compounds exhibit stereoisomerism. What do we mean by stereoisomerism? Different molecules in which the order of bonding is the same, but the spatial relationship among the atoms is different. Stereoisomerism is from this root word isomer. And what are isomers? Isomers are molecules with identical molecular formula but different arrangement of atoms in space. Galactose, fructose, glucose are 3 monosaccharides. They all have the formula C6H12O6. But by the time we look at their structures, you will see that they all have different, the atoms are arranged in different ways. And because of this similarity in molecular or in the molecular formula, but difference in atomic arrangement, these substances are said to exhibit isomerism. Stereoisomerism is generally or broadly divided into 2 types. The first one is enantiomers. Enantiomers. What are enantiomers? Enantiomers are stereoisomers that are mirror images of each other, which are non-superimposable. Too much grammar, abi? Mirror images, you understand what that means? When you say something is a mirror image of something, it means that they are almost exactly identical. But looking at the structure we have here now, this is D-glucose and L-glucose. That is what we use to differentiate different isomers in enantiomers. Sorry, different enantiomers. D-glucose, you see the OH closest or farthest away from the aldehyde group is on the right, whereas in the L isomer, you see that the OH farthest away from the aldehyde group is on the left. And what do we mean by saying they are non-superimposable mirror images? Open up your hand, look at your palm. Your palm look exactly alike, but if you put one on top of the other, you can never, no matter how much, unless you cut off one hand, even if you cut off one hand, you can one thumb can never be on top of the other thumb, and one small finger can never be on top of the other small finger. So you say there are non-superimposable mirror images. You can see them. They are non-superimposable mirror images. The next type of stereoisomerism is Stereoisomerism. In this case, the substances are not mirror images of each other. They are not mirror images. You can see this is D-glucose and D-ultrose. Ultrose is another isomer of glucose. You can see that they are not mirror images of each other. And under this diastereoisomer, we have what we call epimers. And what are epimers? Epimers are compounds that differ at only one point. Look at what we have here. Mannose, D-mannose, D-glucose, and D-galactose. Let's compare mannose and glucose. You can see that mannose and glucose have the same arrangement up from carbon 6 to carbon 3. But at carbon 2, you see the difference. So because the only difference occurs only at carbon 2, you say they are epimers. So mannose is a carbon 2 epimer of glucose, or you can say mannose is a C2 epimer of glucose. Now let's look at galactose. Galactose is another isomer of glucose. They still have the same number of carbon atoms, 6 carbon atoms. If you count, you find out they have 12 hydrogen atoms and of course 6 oxygen atoms. But where is the difference? You will notice that they are all the glucose and galactose are the same except at carbon 4, where the OH of glucose is on the left, whereas that for galactose is on the right, and that differentiates them. And when this happens, you now say that they are epimers. So galactose is a C4 epimer of glucose. Galactose is a C4 epimer of glucose. The next type of isomerism, so look at this. Epimers are diastereoisomers that differ in congregation only on one asymmetric carbon. You can see it. D-mannose differ from D-glucose only at carbon 2. D-glucose differ from D-galactose only at carbon 4. But of course, mannose and galactose are not epimers because you can see that they differ on 2 points. They differ here, carbon 2 and also carbon 4. So both on their own are epimers of glucose, but they are not epimers of each other. So I want you to note that point. So the next isomerism is the one we call anomers. Anomers are special forms of carbohydrate stereoisomers in which the difference is specifically about the anomeric carbon. I want you to hold that word, anomeric carbon, with your left hand. We shall meet it somewhere else. So what do we mean by anomeric carbon? You see this carbon 1 here. This is the anomeric carbon for this structure, and this is the anomeric carbon for the other structure. For an alpha D glucose, the OH group is facing down, whereas for the beta D isomer, it is going up. So you can see that every other thing is the same except on that anomeric carbon. So these are called anomers. So let's take another pause, and C, this class activity. Using structures only, show the difference between glucose and mannose. What is the name given to the type of isomerism between glucose and mannose? I want you to answer this question briefly. Good. So, in summary, we have been able to define carbohydrates. We have talked about the functions of carbohydrates, and we have talked about the forms of isomerism, stereoisomerism exhibited by carbohydrates. I hope you have learned one or two things from this. For listening.